So,
because I just want to show how you play this guy.
Maybe if it's someone who like purposely gets 0, then they just want 10% off.
That does make kind of sense. If you're purposely getting a 0,
Or if they don't care,
Yeah, like they're like, oh yeah, I don't care, I can get a bad grade, I get 10%.
But see, now I am in a position where I have like,
you feel like it's wrong, so you don't want to do it.
But
at the same time, everyone else's grades are going to go up, and so it's going to affect you.
And at the
Like
same time,
drugs.
also we're like, we need to raise money.
So essentially, it comes down to that if you don't, if you're not willing to pay $5 for a grade,
that's $5.
then everybody else gets an advantage over you only because they paid money.
That's not.
Absolutely not.
Or act, or like train
So,
after.
anyway, back to this.
you
Okay?
don't need money for junior, senior.
We do, because our class is freaking huge.
Alright, so
Yes, you do. You
So
have
you have
to
more
pay
money
for
coming into your class.
there are
everything.
better ways to fundraise.
You
Just
sell
saying.
grades, sell Girl
I'm
Scouts.
not saying we're doing it the right way. I'm telling him we need
Yeah.
money for it.
Yeah.
I already said sell drugs.
Yeah, let's sell drugs. Drugs. I like drugs.
Well, that's what we're coming to, guys. So, anyway.
Well, I came on about chemistry.
So, we talked about equilibrium. This whole chapter's been about equilibrium. We talked about how, in specifically this section, we're dealing with the equilibrium of what?
Rates.
No. In this particular lesson, yesterday.
Dissolvation.
Dissolving, right? Where we're talking about the equilibrium associated to dissolving a salt. Okay? There is a point where you cannot dissolve any more salt, and that is your equilibrium point, also known as your saturation point. Okay? Some things dissolve easier than others. Okay? We talked about when you reach your saturation point, you are producing ions as fast as you are taking those ions and going back to the solid form or precipitating them. So the two processes are dissolving and turning into ions, and precipitating, turning back into a solid. Okay, then we briefly talked about the equilibrium expression really is no different, but because we can always remove that solid, they do give it a different name, and they call it the solubility product because it ends up being just the product of your products. Right? Multiplying your products. Okay. Then we talked about what a big KSP versus a low KSP meant. And I gave you an example of, let's say, table salt is dissolved or is put in water. It breaks up into its ions. Whenever you dissolve something, you are breaking up into the individual ions. Okay? If I say that the KSP is very large, what does this tell me?
That there's more ions dissolved.
Okay? Product favored, more ions dissolved, which means you have a lot of ions in solution. Okay? Which means most of it or a lot of it, I'm not going to go ahead and say all of it, it depends on the situation, is in ion form. Okay? If you have a KSP that's really low, we probably will say it's relatively insoluble or not very soluble because you have mostly solid and not very much ions. And if you have mostly solid, it's just going to sit at the bottom of your beaker, and you won't have any ions dissolved in solution. Does that make sense? So just a quick review from yesterday. And I showed you this example. In here, most of them dissolved, and in this one, only one of them turned into ions. So one dissolved more than the other, more soluble versus less soluble. And what you see then is the K value is larger for the more soluble thing. You what? You're not going to,
No. No.
Oh, it's a pre-release at 10.
leave your backpack then.
And your phone.
And your phone. There you go.
That'd be really awkward if he said he valued education, then we did do that.
Oh, great.
Sort of. Alright. So then we said, with this information, if I have KSB, I can find solubility, and if I have solubility, I can find KSB. Do you remember what I said solubility was essentially? Molar concentration. So the concentration of something in molarity, and we can replace that with our brackets and our KSB expression. So for this particular case, these brackets represent molar solubility or molar concentration. So I can replace solubility with the brackets. They mean the same thing. And then we began to do that, I believe, in this particular problem. We wrote the equilibrium expression, and I don't know if you guys remember it, but I put S and S, and then we squared them. And then Gage made that whole deal about how it would be easier just to plug that in. And in this case, yes, but when we get to more difficult cases, it was a little bit more challenging. And we got that. Then we did this one. This one was more challenging because of what? It's not a 1-to-1 ratio. So if I have 1 molar of this, I have 3 molar of this, and 2 molar of this. We talked about S, 3S, and 2S, correct? So there's your equilibrium expression. Okay, put in the KSB. If we have the KSB, we should be able to find solubility. And we said this was 3S, so when we plugged it in, remember solubility and concentration are equivalent here, so I can replace them. 2S was put here, and then we simplified.
Wait, why did you put the exponent there? Why is there
Which exponent? 3 from there. 2 from there.
Why did you keep the coefficient? If you just put it as an
Because when we're writing the equilibrium expression, the exponent comes from the coefficient, but we also got to take into consideration when this breaks apart, it breaks up into more particles. So it's twofold. Okay? Then we simplified it, I don't know if you guys remember, to 108 S to the 5th. Okay, you have to take the 5th root, or another way would be raised to the power of 1/5. Okay? What's the matter, Kate? Oven. Okay. Did we do this one? Okay. We'll start with it. I'm trying to get done a little early today so I can give you some time to work on homework in class. We'll do our best here, but. Is this one actually in your notes?
This one is. Yes.
Okay, cool. Okay? So, it says given that the KSB value of silver chloride is 1.8 times 10 to the negative 10, find solubility, or solve for S. Okay? So, first thing I should probably do is write the equation for that dissolving. Think you can do it? What is silver? Okay, what is its charge?
3 minus plus.
Why?
Because it says.
Because it tells us the oxidation number.
That's
Oh, I was thinking of L for.
I didn't think you had to write it down.
Wow, you'll see. Okay? And then chlorine minus. So since I say 1 and 1, you would just crisscross ones and you would leave them. So it is just AgCl. So this is going to be an easier one because of the 1-to-1 ratio. So this one shouldn't be too difficult to break apart into its ions. What's the matter?
He's trying really hard.
So how did we get rid of the
I was going to.
positive and negative?
I knew you were gonna ask that. So I was gonna leave my backpack outside, so I was just gonna drop my phone and then do my laptop. Then I was like, nah.
You were just talking about how you value your education a second.
Well, I knew it was review, so.
Oh, myself.
Okay. So,
How do we get
this is going to break up into its ions. What?
How do we get rid of the positive and negative?
So this goes back to a while ago when we wrote chemical equations. When it was ionic, we wrote the oxidation numbers and we crisscrossed them down. If there were ones, we didn't write them. If we could reduce, we would. Like if this were a 2 plus and a 3 minus, the 2 would come here, the 3 would come here. Do you remember that? Okay. So then, since it's a 1-to-1 ratio, we can write the ions probably pretty quickly because there's the charge. So this is when it's combined. This is when it's in its ion form. That's why you see the charge here. Okay, this one isn't overly difficult because everything is a what ratio? 1-to-1 ratio. After I write the equation, I should probably write the expression because that's where I'm going to be able to convert KSB to S or S to KSB depending upon what they give us. So if we write the expression, what does it look like?
S.
What?
Just SS.
In this case, yep. Since all of them are 1-to-1 ratios, they all have the same solubility, so I can just go ahead and plug S in. If you want me to actually write it, these are all S's. And we said solubility and concentrations are equivalent, so we can replace them. And they gave us KSP, correct? Here's a little hint for you. Little quick hint. Whenever you are solving for solubility and it's a 1-to-1 ratio, it is always the square root of your KSP. But that is only if you're solving for solubility, and that's only if it's a 1-to-1 ratio. Because if it's a 1-to-1 ratio, it's just S's, right? And it will be S times S, which is S squared. If it's not a 1-to-1 ratio, it will not be the square root of, yes, I do not have my loop.
I wasn't looking at that. I was looking at the ground.
Whatever.
again?
No, I think
I was just looking at the ground, just dozing off. Thinking of what could have been.
Oh my.
And I was going to tell you that Supreme always drops on Thursday. But it's Supreme this time.
So you were gonna try to.
But there's no, on the website, there's no way I was going to get them. I was going to try it out.
Wow.
I already took an L this morning at 9. During the passing period though. Took an L.
You trying to buy them for
Basically. So many.
Okay. What do you guys get for the solubility?
1.34 times 10 to the negative.
And that is going to be with what unit, do you think? Yep. Because remember, solubility and molar concentrations are equivalent.
How did you do that?
Square root of 1.8 times 10 to the negative 10. Make sense? Okay, let's do one a little bit, well, this one isn't any more difficult. Why don't you guys, well, why don't you guys, do you guys know what carbonate is?
CO4.
Nope.
3. CO3.
303 what? 2 minus. I want you guys to do this problem. I just told you what carbonate was. You should be able to write what copper carbonate is and then break it down into its ions.
What are we doing Thursday?
Remember. Start working, guys. Come on. I just wrote it.
Oh.
Yeah, there you are.
Wait, let me crisscross.
So if it's a 2 plus and a 2 minus, they reduce, right?
Yeah.
So you just put CuCO3.
What chapter is this? Third.
You're not real prepared today, are you, Marty?
I could have sworn I had it.
Chapter 15.
Oh, one is inside. Okay. More.
Confused?
Just one day.
Here again.
Are there supposed to be coefficients?
And turn.
Wait, oh wait, no, it's, why don't you put 2 minus
2 minus 2 plus, they cancel out. You got an answer yet?
Do those cancel out?
You can cancel out. Okay, first thing you should always do is write the equation. Second thing, write the expression. There's our expression. Solids are not in it, correct? What's the matter?
Where'd you get calcium? It's CD.
Oh,
That's got my.
sorry. That kind of looked like an A because I didn't, that's what I do.
What's going on here?
Okay? Now, notice the ratio. What is it?
1 to 1.
1 to 1. I said if it's a 1 to 1 ratio and you're solving for solubility, really the answer is just what? Square root. Now, how this works is S, S, and S, correct? So these are S's. So your KSB equals S squared, and you know your KSB, take the square root of it, and you have your answer.
1.58 times 10 to the negative 5th molar.
So approximately 1.6 times 10 to the negative 5th. So what that's telling me is exactly how many ions I have dissolved. I know that I have this many moles per liter of each of these ions in solution at equilibrium. That's its saturation point. I cannot have any more. So for example, if I were to do an experiment and I were to calculate the concentration of ions in solution, if it were greater than what the K value said they should be, I would be supersaturated. If it was less than what the K value said it should be, you're unsaturated. And if they are equal, you are at your saturation point. And that's what this next question is going to ask. And I think I have in your notes, it says determine if it's saturated, unsaturated, or supersaturated, right?
Yeah.
Okay. So, last problem here. Right? It says zinc hydroxide. Man, I wish we would have paid real good attention when writing and balancing chemical equations, and memorizing polyatomic ions.
2 is Arno.
I did it?
Yeah.
Oh yeah, put zinc 2 hydroxide in your notes.
Hydroxide.
Okay? So what is zinc?
DN.
What's its oxidation number?
2 minus
2 plus. Positive guys always first. Cation first, then anion. If they give you Roman numerals, that tells you the oxidation number of your metal. And the reason why it does is because, will the periodic table tell you the oxidation number of zinc?
No.
No, it will not. So, that's why they give you the oxidation number.
Is the second one OH?
Well, that's how you're really feeling.
OH minus is hydroxide.
Yes.
Now in this particular situation, it's not 1 and 1, or it doesn't reduce. So you would do what?
Cross them.
Crisscross them, but I need parentheses because it is a polyatomic ion and I have more than one of them. If you do not put the parentheses, you are saying zinc is bonded with a weird way of writing water. OH2. So So there's my solid. Okay? Now, this is going to be a little bit more difficult to break up because it's not a 1-to-1 ratio. Zinc. What's his charge?
+2.
Crisscross if you forgot. And hydroxide is a polyatomic ion, so we do not break it up. It has a 1- charge, but however, how many of them do I have? So it goes as a coefficient. There is your balanced chemical equation. It does take practice to get good at writing ionic equations or dissolving equations. Okay? What is the next step?
Right.
Expression.
Okay, write the expression. So KSP is equal to it's squared, correct? Everyone following on why that is? Okay? Then I want to replace these with what their variable S
S.
represents.
S
To the
times.
third.
S
So
one,
this is
S
S, and this is
S squared.
not S squared,
2S.
2S.
What?
Wait, but isn't it also squared?
It is. But yeah, we will only see that once we plug it in.
Oh, yeah.
So KSP is S times 2S squared.
Why is it 2S?
Because you square it, because that's how we do equilibrium expressions, and it breaks up into twice as many particles. So I need to account for the fact that it breaks up into twice as many particles, and for the fact that equilibrium expressions are written with exponents as subscripts, or exponents from the coefficient. Let's simplify. You haven't seen one like this yet, so let's simplify this. What does this simplify down to?
4S squared.
4S squared. You gotta take the 2 and distribute to both the number and the variable. So it's 4S to the second power times S would be
4S.
4S to the third, right?
That's what I got.
S times S squared is S cubed. 2 to the second power is 4. Okay? I'm gonna write it over here so I have a little bit more space. Now, do they give us S or do they give us KSP? They gave us KSP. Now, could they have given us S? Is it possible? They could have told us what the solubility is.
Yeah.
And we can plug it into S and find the KSP. That's where that one slide that said if you have KSP, you can find solubility. And if you have solubility, you can find KSP. Depends on what they give you, but the process is the same for both, correct?
Why does it say calculate the KSP? They gave us the KSP.
Oh, yeah, they did give us
Oh.
solubility. Sorry,
Oh.
I didn't read the problem. Okay, and how do I know they gave us solubility?
Because it's calculated.
Polarity.
That makes sense? So that is our what? This number is our what? That's our S. Did all what for nothing? Good job. Why is that for nothing?
No, it's not even the right thing to do.
Oh, so you plugged in for KSP? Yeah, be careful to read what it is they give you, because they could give you KSP, they can give you S.
6.25 times.
So it'll be 4 times,
Oh, wait.
Is it the same thing?
Calculators have matters.
okay, what'd you guys get?
6.25 times 10 to the negative 17.
So this is my experimental, this is what I did, experimental K value. Okay, I'm going to give you the theoretical K value. Your theoretical K value is this.
Is this just a random number that you're making up right now?
I don't know if it's the actual one or not. It's what I have in my notes, but I want you to figure out if this is a supersaturated, saturated, or unsaturated solution.
How do you know if it's saturated or supersaturated? Like, what's the difference in that? Oh, wait.
Okay? Well, think about it. Remember what the KSP expression is. KSP is really the concentration of your ions, right? Right? That's what the KSP is. So, the theoretical is what your saturation point is, or the maximum amount of ions you can have in your solution at a certain temperature. Okay? So if this is the max I can have, is this bigger or less than?
Way bigger.
It's bigger. I wouldn't call it way bigger, but it is bigger. So what that means is, in order for this to be bigger, you would have to have more ions, right? More ions in solution than you theoretically can hold would mean it's a what kind of solution? Supersaturated. So if you ever ask the question, saturated, unsaturated, or supersaturated, you're going to compare what you got experimentally with what the saturation point is. The theoretical is always the saturation point. So what if these were equal? It would be saturated. Does that make sense, everybody? So, what we've done today is we've mathematically figured out how to find the K value when we know the solubility, and how to find solubility or concentration of something, how much will dissolve, if we know the equilibrium constant. Okay? So, I have a worksheet. Oh, shoot, it doesn't give me that much time today.
I text my dad.
77.
What'd you say, Gabe?
I text my dad.
Is he in on this too?
No, he needs my eBay login. I don't know what it is.
So that first question that is on your worksheet here is an example of the question we just did, except for you're not solving for anything, they just gave you the numbers. Then, number 3, you're writing the KSP expression. Number 4, you're calculating for solubility S. And number 5 is a tricky one. And I'll be surprised, I don't know. If you get that one right, you're getting it. Because I didn't show an exact example of number 5.